This is a question from AQA A-level Chemistry. It's from paper 3. It's a required practical based question, and this is focused on RPA8. As always, I'm going to recommend that you pause, have a go at the question for yourself on each stage, and then review your answers at the end. So let's start by taking a look at part A, then parts B and C, then we've got parts D and E. And now you've had a chance to look, let's go back and see what we can do. So, iron used in the construction of pipes, bridges and ships can be protected by attaching a sacrificial anode to the structure. The sacrificial anode is another metal that corrodes in preference to iron, keeping the iron structure unaffected. The metal has got to be a stronger reducing agent than iron. In old terms, you're thinking about it being more reactive, and that's where you first came across sacrificial protection, higher in the reactivity series. But we're going to use this data to help us to understand this. The table gives us standard electrode potentials for some common metal electrodes, and your job is to use the standard electrode potentials to identify the most effective metal for using as a sacrificial anode for iron, explaining your answer. So what I'm going to do, I'm going to take a look at the copper and the magnesium. And the reason I've chosen those is one of them is the most negative value and one of them is the most positive value. You'll know that very often these tables are put in order of size or magnitude. Sometimes that does not happen and you need to be prepared for it. Now, the reason I've drawn this number line is because what I'm going to show is that the electrons are going to flow from the left to the right. That is always the case. And that means that we are, in this particular circumstance, going to reverse the magnesium half cell equation because they are always provided as an equation for reduction, but oxidation always happens at the half cell on the left hand side of the number line. That means that my Mg goes to Mg2 plus 2E minus. Now, in a sense, if that is the metal that is to the left of copper, which is most positive, it's also the most negative. So it is going to be to the left of absolutely every other metal. That means it's the most powerful reducing agent out of all of the examples we have. So that's the reason that we choose that one. Moving on to parts B and C. In B, the pH of seawater varies between 7.5 and 8.4. An aluminium sacrificial anode slowly corrodes during its use, and when attached to a ship, when it comes into contact with seawater. The aluminium sets up a cell between itself and the iron structure. In this cell, oxygen dissolved in water is reduced to hydroxide ions on the iron surface. This oxygen hydroxide electrode has a standard electrode potential of plus 0.4 volts. Write a half equation for the oxygen hydroxide electrode reaction. Construct an equation to show the overall cell reaction involving the aluminium anode. Use the table and information above. So I'm going to bring that in and I'm going to leave that on the left hand side. So let's start by looking at the information that we have. We know that we want a reaction where oxygen dissolves in water and is reduced to hydroxide ions. So we're going to build that half cell here. I've already, you can see, I've put the 2H2O in there because of the two O's. We are going to need to multiply that up, but then that means we are going to make 4 OH minuses. Now that also means that we need to balance it only with charge, so we add 4 electrons on the left hand side. So it's O2 plus 2H2O plus 4E minus goes to 4OH minus. We also need to combine that with the aluminium ion being reduced to aluminium. So we're going to take a look at the half cell for that one. And we've got Al plus 3E minus goes to Al. I'm now going to build a number line with both of those things in. And you can see I've squeezed this into the top. Negative 1.66 is the most negative on the left. The most positive is on the right. So I've put in what those half cells are. And we know on the number line, electrons will always flow from left to right. They'll always go from most negative or least positive to most positive or least negative. So electron flows in that direction. As a result, we know that whatever is on the left is not going to be reduction. There are electrons being lost. So we have to reverse the equation that has been provided. The Al plus 3 E minus goes to Al is what came in the table, but we are going to switch it to Al goes to Al plus 3 E minus. So I've put in now the half equation that we'd already worked out over on the left-hand side, but I've also then had to combine those two. I've got 4 electrons on the oxygen and water half cell. I've got 3 on the other, and we need to get rid of all of them, so we need a lowest common multiple. Easiest way is to multiply them up to 12. So you can see here we're multiplying the top half equation by 3 and the bottom one, which remember we've also reversed, by 4. That then allows us to see the completed equation that we can see here. Finally, cell EMF. Well, we have gone from negative 1.66 volts on the left to plus 0.4440 on the right. That is a difference of plus 2.06 volts, so that's the EMF that we want. On to part C, give 2 reasons why the value of the cell EMF you calculated would not normally be achieved when the cell operates in seawater. Well, we know there are certain standard conditions. 298K, 1.00 molar solution, 100 kilopascals of any gas. We are not going to have standard conditions in seawater. It's also relating to another area of the course, the fact that we're dealing with aluminium ions, which have quite a specific circumstance, and that is that they can react with acid and alkali. There is amphotericity. So it's accepting that the Al plus 3 may actually react in alkaline conditions. Moving on to, finally, parts D and E. To examine the effect of a sacrificial anode, a student carefully cleaned a piece of iron foil and a piece of aluminium foil, joined, placed in a beaker containing a buffer solution at pH 8.0. Air bubbled steadily into the solution. At intervals, the foils were removed, separated, dried, and weighed before going back in the buffer solution. Explain briefly the results obtained for the iron foil, which we can see here has stayed constant. Well, earlier in the question, we did speak about sacrificial protection. Sacrificial protection does mean that the more reactive metal, the metal that is more likely to be reduced is going to be. So that's what will react first. So the aluminium mass has gone down, but the iron will stay largely the same. Why would the aluminium foil stop decreasing in mass after a given time? Now, this again relates to wider knowledge of chemistry. Aluminium will usually form a protective oxide layer. So over time, a protective coating will form on the aluminium surface that will prevent the reaction from continuing. That takes us to the end of this question. Thank you for listening and goodbye.